YouTubers, this is Brendan, and this is going to be another physics video to help you through your course. So what we have here is a very common physics problem. What we can see is that we have a block that is sitting on a 30 degree inclined plane. So very common type of problem, and we're going to go over kind of what are the steps to handling this, and I'll try to break it down as clearly as possible. So the problem reads, a 10 kilogram block sits on a 30 degree inclined plane. Coefficient of kinetic friction is 0.15. Determine the acceleration of the block down the plane. So I always think it's a good idea to organize what you're given. So in this problem, I'm going to go ahead and say the mass is 10 kilograms. Let me change the pen stroke really quick. So the mass is going to be 10 kg. The coefficient of kinetic friction, that's mu sub k, is going to be 0.15, and that's dimensionless. And the angle theta is going to be 30 degrees. So step one for this type of problem is to define your plane. So define your plane. And typically what you do for this type of problem is you tilt the axis. So I'm going to say define your coordinate plane. And what we're going to do in this case is we're going to draw a dashed line this way. And that's going to be our x-axis. And our y-axis is going to be completely perpendicular to our x-axis, as it always is, but it's off on a plane like this. So that's step one, is just to set that up, and you'll see why that's so valuable soon. Step two is to start thinking about your free body diagram and think about all the forces that are acting on this block. So this is always a good idea anytime you have any problem that involves forces. We know this problem involves forces because it's asking for acceleration. So what forces are acting on this block? Well, the only forces that are acting on the block have to be either field force, or they have to be forces that are in direct contact with the block. So I'll go ahead and identify those as the force of gravity and the force of the, essentially of the slant here on it, which we call the normal force. So when I set up the free body diagram, I'm going to see two things. One, the force of gravity acts straight down, as it always does. And the normal force is going to act to a right angle to the surface. So it's going to look something like that. So this would be our normal force, and that would be our force of gravity. Now, unfortunately, it's not super useful to think of things when they're at slants to each other, so what we have to do is resolve the components. So what I'm going to do is just kind of identify what the force of gravity is. In this case, it's mass times g, so 9.8 times 10, and I'm just going to round that to 100 for the purpose of this problem. So the force is going to be 100 newtons, and that force is going to act straight down. So I'm going to go ahead and draw that on this block up here. So that's a 100 Newton force acting straight down. Now, we can't figure out the normal force because we don't really know anything about it yet. But what we do know is that it's usually a good idea to resolve our forces into the x and y components, and we can go ahead and do that pretty easily here for this force of gravity. Notice I'm drawing a right triangle, and the key thing that I want to emphasize is that the right angle is opposite the hypotenuse. So if the 100 newtons, that's your force of gravity, that has to be the largest force because any component of a force has to be less than the force itself. I can't have a force of 500 newtons and then have a component of that force be 600 newtons. It just doesn't make any sense. So this is a property from geometry that comes next, that this triangle, the large blue one and this yellow one here, are similar. So if that angle is 30 degrees, this angle is also 30 degrees. So what we can do is figure out our force of gravity in the x direction and our force of gravity in the y direction. So that's fx and that's fy. And we do that simply using trig functions. So I'll put step 3, resolve components. Resolve components. So what we can say is that the sine of theta is equal to the opposite over the hypotenuse. And in this particular triangle, our theta is 30 degrees that we're looking at. And that's going to equal the opposite, which is f of x, over the hypotenuse, which is 100. Now, we know sine of 30 is 1/2 from pre-calc, or maybe algebra 2 if you touched on it there. And then 100 is down here, so we bring the 100 up, and we would find that our force in the x direction is equal to 50 newtons. So this value right here is 50 newtons. Now we could do something similar for our force in the y direction. We would do sine of theta is equal to, cosine of theta is going to equal the adjacent over the hypotenuse. So then cosine of 30 degrees would equal f of y over 100. Cosine of 30 degrees is root 3 over 2. So that's about 1.7 over 2, so it's about 0.85. So I'm just going to say the force in the y direction is about 100 times 0.85, so that'd be 0.85 times 100, and that's going to equal 85 newtons. And so I'm going to say this force is negative because normally we would define down as being the negative y direction, so I'm going to say f of y is negative 85 newtons. The next thing that we're going to do is we're going to apply Newton's second law, and that is that the summation of the forces is equal to ma. Now, when you have multiple angles going on in the problem, it's very wise to go ahead and break this up into the summation of the forces in the y direction equals ma, and then over here the summation of forces in the x direction is equal to ma. So what we can see in this problem is we have two forces acting in the y direction. We have the normal force, and we also have the force of gravity in the y direction. This box isn't going to accelerate off the plane. It's not just going to jump off of that ramp. And we also know it's not going to fall through it. So what we can say because of that is that the summation of forces in the y direction is equal to 0. So we have two forces in the y direction. We have the normal force, and we have the force of gravity in the y direction, which I'll define as this. And we know the value for force of gravity in the y direction. It's negative 85 newtons. So what we can see is that the normal force is also equal to 85 newtons. And that's going to help us as we go to the summation of the forces in the x direction. Now, in the x direction, we have two forces, and I did forget to put this force here at the very beginning. One force we have is the force of friction. The force of friction always acts opposite the motion. If this box is sliding down the plane, the force of friction would be opposite that, going up the plane. So if our summation force in the x direction equals ma, we know that we have two forces acting in the x direction. We have the force of friction, and we have the force in the x direction of gravity is equal to mass times acceleration. Well, the force of friction can be expanded into mu times the normal force. And we know what this force of gravity is in the x direction. We know that this is just 50 newtons. And I'm actually going to say it's negative 50 newtons because it's going to the left. And that's going to equal the mass times the acceleration. The mass of the box was 10, and the acceleration is what we're solving for. Now, we said earlier the mu value was 0.15, so this becomes 0.15 times the normal force, which is 85 newtons, minus 50 is equal to a. And what I'm going to do is I'm just going to go ahead and bring that 10 over here so I can isolate the a variable. So 0.15 times 80 is, let's see, what is that? That's, calculate that really fast. It's 12. No, times 85. It's 12.75. So your acceleration is going to end up equaling 12.75 minus 50 over 10. 12.75 minus 50 is going to be negative 37.25 over 10 is going to give you negative 3.75, and we know the units meters per second squared because everything else was in standard units as far as newtons and kilograms. So that's pretty much it. That's how you set up a block on an inclined plane, and I hope you found this video helpful.